Welcome everyone to my YouTube channel, Durvil. Today we're going to talk about JFET characteristic and parameters. Let me remind you what we talked about last time in the previous video. In the previous video we talk about the two big concepts of FET, that we have junction feed effect transistor and metal oxide semiconductor FET. And then we said that let me focus on our JFET transistor, on JFET, the junction feed effect transistor. We said that we got two types, N channel and P channel. Guys, for those who want this document, I will send to those one who subscribe, because I can see their email address here. But for those who didn't subscribe, I don't know how I'm going to send it to you, but you can write on comment or send me your email address and I will forward this thing to you. This document is very important, summarizing a lot of things here. And then we say that VDS control the drain current. When the VDS is increasing, the drain current decrease. When the drain current, when VDS decrease, the drain current increase, which is ID. And this was the logic symbol that I showed you last time, which is a N channel, which the arrow is pointing in, P channel, the arrow is pointing out. So now let's talk about the JFET characteristic and parameters. So let's use this sketch of mine here. Now on this other side, on my left side, regarding the way I'm sitting here, it's a circuit, this circuit that representing the VDS is equal to 0, because we don't have any voltage at the source. Even at the gate there's no voltage this side on the two sides. And then we have a various VDD. In this case VDD is equal to VDS. And on this other side we have a graph where we have two axes, ID axis for drain current and the other side for V for the voltage, which is VDS. And then in this graph we got three regions. We got ohmic region, action region, which we call sometimes pitch off region, and the other side we got the breakdown region. And we got these other parameters, that is IDSS, which is the maximum value of ID. And then we on the other side here, down here, we got the pinch of voltage, which is VP. And then here we just wrote VGS. We got this type of drain characteristic and VGS is equal to 0, which is, so when VDS is equal to 0, ID is equal to IDSS. So the current is at the maximum value, which is IDSS. That's why I say IDSS here, it's a maximum value of ID, and it's allowed a specific for the condition for VDS equal to 0, and VP is the minimum value of VDS at which ID become essentially constant. So guys, VDD it's a value of VDS, a minimum value of VDS. So what happened in this circuit? When we start, let's start at A. At A, everything is 0. We don't have the voltage. VDS is 0. So even we measure any voltage, even we measure the voltage anywhere here, we don't have a voltage. Every voltage will be equal to 0, cause no current, no drain current flowing. Let's say we increase this VDD in the small amount, let's say less than 1. What will happen? It's going to generate a small amount of drain current, which is ID. And then what will happen now? There will be a small penetration of depletion in this ohmic region, which it will be a considerable amount of depletion. So it's an insignificant amount of depletion, so doesn't affect the transistor. So in this type, in ohmic region, the transistor behave like a resistor. And then when we keep increasing the voltage, what will happen? The drain current, which is we represent here using this green line, ID, the drain current will increase. By keeping increasing VDD, the drain current will increase until we reach the point B. At point B is this time the depletion region get in now in the what we call the action region. At point B this time now we get in the action region. That now any increase in VDD is no longer going to affect the drain current, because the drain current reached the maximum value, which is IDSS. So by keeping increasing VDD, nothing will happen to the drain current. The drain current will stay constant, no change. Keep increasing VDD, which is VDS also, the ID will no longer change. The drain current will stay constant until we reach point C. At point C you can see the curve change, the curve get increased again. Now ID increase now rapidly. This can happen when the breakdown region with the depletion region, because the depletion region we talked last time in the video here, which was the depletion region, is that time the P and the N channel get formed. So the positive ion and the negative ion would form the depletion region. So we get this time. So by getting at point C, what happened? This region will break down. So that they call it the breakdown region. That can happen if the JFET get damaged. Yeah. Where the JFET get damaged by keep increasing the VDS, which is VDD. So please remember IDS has the maximum value of ID. It's going to be very important, and V pitch, which is the pitch with the voltage of the voltage or the minimum voltage of VDS, that which is the fixed value, it's always there close to 0. Even 1000, 1 million is always close here to 0. So now let's see, now we take an example of VDS, because by the time VDS will be equal to 0, because it's an N channel, so we're going to have a negative voltage here this side. Let's say now put a voltage this side. What happened here now? So when we have a various voltage, a negative voltage, which is VDD here, so what happened when you keep increasing VDD now? What will happen? Because we say that when we keep VDD here, what will happen? VDS will increase, obvious. And then what we say that when VDS increase, what happened? The drain current decrease. So what happened here? When we increase VDD, what happened? Current decrease. Let's say VDD, the case that I just explained the case when VDS is equal to 0. But let's say now VDS is equal to minus 1 volt. What will happen? The drain current, which was here on top at IDSS, will reduce somewhere here. So you can see now. And then if I keep increasing VDS, the current will keep decreasing until we get this maximum value of VDS that the JFET requires, which we call the VDS off. Because the VDS off operate, so the JFET operate between 0 if we check the ID side, the drain current side is operate when ID is equal to 0 and IDSS, and on the VDS side is operating between 0 on the VDS axis is operating from, on the VDS voltage is operating from 0 to VDS off. So when we reach VDS off, which is the maximum value of VDS that the JFET requires, so ID will be equal to 0. That's why this is a family of drain characteristic curve, because this side we just represent when VDS is equal to 0, but we have a case where we have a voltage on this side. So we're going to see step by step how the current is decreasing, is reducing the amount of the drain characteristic curve. So now what is VDS? Let's talk about these parameters that we just talked about now, which is VDS off. Now we say the VDS off is the value of VDS that make ID approximately equal to 0. It's a cutoff voltage. You can see now in this curve, we can see ID, because this blue line is representing the value of ID, this blue curve. So you can see ID here, because of VDS is close to 0, which is say it's close. That's why they say approximately equal to 0. So that's why we represent this thing down here, because further guys, they're going to tell you to draw this drain characteristic curve. So you must draw for the ID is equal to approximately equal to 0. It's going to be close here to 0. So We must know also, we talk about pinch off voltage, which is Vp. We must know that Vds and V pinch is the same value but opposite sign. So for example, V pinch when it's called V pinch, when V pinch is equal to 3, Vgs off is equal to -3. When Vgs off is equal to 5, V pinch is equal to minus 5 volt. When V pinch, let's say V pinch is equal to 10 volt, Vgs off will be equal to -10 volt. So you can see it's always the same value but opposite sign. But guys, before we move to that question, our example 8.1, sorry, I'm going guys to explain you these two concepts. Guys, you can see sometime we're going to talk about VDD is equal to VRD minus VD sorry, it's plus here, please. Now I remind, it's plus here, it's a mistake, please remember, plus here. So we're going to talk about sometime when VDD is equal to VRD plus VDD plus VDS, and VDD is equal to VRD plus VD. Sorry guys, I want to remind you again, plus here is just a mistake of mine. So what happened, this thing, when you don't have a resistor here, we're going to measure this voltage here, we call VDS. That's why we say VDD is equal to VRD plus VDS. And this side, when you have a voltage, VDD will be equal to VRD plus VD, the terminal voltage. So now let's move, and then VDS, we can calculate VDS by saying VDS is equal to VD minus VS. Let's move to this example 8.1. So now this example, check this voltage. So now automatically this question here 8.1 from your textbook is the question. They said calculate VDD, determine the minimum value of VDD required to put the device in the constant current region operation when VDS is equal to 0. And then they say VDS off is equal to -4 volt, IDSS is equal to 12 volt. So what happened here, they already tell us VDS is equal to 0, which means already ID is equal to IDSS, because we're at the maximum regarding the curve that they give. You can see how this thing is fantastic, guys. You can see it's very simple and fantastic. They say VDS equal to 0, which means ID, we are at the maximum, ID will be equal to IDSS. So which means in our question here, we don't even need to stress now to find the value of ID, because we know that ID is equal to IDSS, because VDS is equal to 0 regarding the question that they tell us. So what happens, so which means that when if let's say VDS equal to 0, we know at VDS regarding that curve, at VDS, that's why I represent that curve again. Regarding the curve, we said that at ID is equal to IDSS, we know that we talk about V pinch off is always there also. So let's talk about if there's no something that is telling us that where we can get the value of V pinch, and then we come in the question, we realize they say that VDS off is equal to -4 volt, but I know VDS off is equal to V pinch off but opposite sign. So automatically I know already V pinch off is equal to 4 volt, because VDS off is equal to -4 volt. Guys, can see how this thing is very nice. And then now I know what is VDS off, what is V pinch. I said that V pinch is the minimum value of VDS at which ID become constant. It's the minimum value. So which means V pinch is it's part of the scale. It's part V pinch of it's part of VDS. It's a scale of VDS, like me having 2. Let's say I have 2, I have a 0.2 here, 0.3 here, but in this case we don't have it, so we have only one scale here, which is 2, V pinch off. So I can say VDS off, it's equal to V pinch. It's equal to V pinch. So I won't strike anymore. I won't strike anymore. I won't strike anymore now to find VDS. Automatically, let me come here in our question here. We're solving this question. Let me erase this thing. Let me erase this part. Sorry. Yeah, let me make this thing clean. Yeah, let's come here now. So now automatically I know that my VDS will be equal to V pinch. My VDS is equal to V pinch, because what did they say? V pinch is the minimum value of VDS, and then we have only one scale here, which is V pinch. So I can deduct VDS is equal to V pinch off. So now I can say VDD, because we don't have a resistor here, VDD will be equal to VRD plus VDS, and VRD is equal to what? Is the current this time, this voltage that we measure here, it's a current times the resistor, which is ID times RDSS times RD. And then I say ID is equal to IDSS. ID is equal to IDSS because VDS is equal to 0, because regarding the question that they give me. And now automatically it's going to be what? 12 times 560 plus VDS. But some people after reading this question, they already tell you that there's some people after reading this question, because they already tell you VDS equal to 0, they like to complicate themselves and in coming themselves and coming and break their face again here using this method of saying VDS is equal to VD minus VS, and then they get stuck by finding again VDD and RS. Automatically, guys, when you don't have a resistor here, don't even think about this method, because you're going to get stuck for nothing and waste time, because this question can come, you need to solve this question for 1 minute or 2 minutes, that you're going to take maybe 5 or 10 minutes, start asking yourself question, why I don't have RS. Though automatically, guys, must come here and deduct like VDS is equal to V pinch. Like I say, VDS will be equal to V pinch, which is equal to 4 volt. And then I just replace, and then I got 10,7 like in the textbook. Let's solve now this question. Now the same question, VDD question. They say what's the related problem? They say VDD is increasing with 15 volt. What is the value of drain current? The value of drain current regarding this question that we solve. Let's come back here, guys. If we increase VD, we know that VD we already here, because we got 10,7. we already here. But if we keep increasing VDD, what will happen? The value of ID will stay constant, which is equal to 12 milliampere will stay constant. So that's why I say ID will remain approximately 12 milliampere, because any increase, because VDD here it's already, we got already at point B. When VDD is 10,7, we are at point B already. So any increase, ID will stay constant here, approximately constant. So between B and C, approximately constant. So guys, let's solve now. Let's see question 8.2. Question 8.2. Let's see question 8.2. Question 8.2, they say a particular defect as VDS is equal to 4 volt. What is the value of ID when VDS is equal to 6 volt? Class, very easy. What did they say? They said that VDS, they say that the drain, they say that the defect operate, this defect operate between this side, between IDSS, between 0 and IDSS regarding the drain current, and then regarding the VDS is going to operate between 0 and VDS off. So if I keep increasing here, what will happen? This side, if I keep increasing, this side ID will stay 0, because what happened? If I increase VDS, what will happen? ID will decrease. So I keep increasing VDS, ID will increase. VDS off, when VDS is equal to 4 volt, which is VDS off, ID will be equal to 0. Any increase again here will no longer affect the current will stay 0. I can't say -1 or -2 or -4, so the current will stay 0. So guys, you must understand how easy this question is. It very easy. Question number 8.2, that's why I explained this side. So that P channel will operate between 0 and IDSS, and between 0 and VDS off. So in this area, so any further in this area in VDS, ID will stay already 0 if I'm at 0, because when I increase VDS, ID decrease. Thank you guys. Don't forget to subscribe and like my video. For those who want this document, please don't forget to send me your email address, or subscribe. I will see your email address so that I can send. It's a very powerful document. There's a lot of things here, a lot of things. The whole chapter 8 is here, guys. The whole chapter 8 is here. If you need that code document, I can forward it to you, but you must subscribe and get, so that I can get your email address. For those who already subscribe, you can just write and comment, and then I will send you the PDF if you want it. Thank you guys. Don't forget to subscribe and like the video. Thank you, bye, and have a good day. I'm coming with another video where I'm going to talk about transfer characteristic curve. I don't want to make long videos. We're going to talk about transfer characteristic curve this side and solve those questions. Also try to explain and solve, because very soon I'm going to start solving question papers. So guys, yeah, I don't want to bother you with long videos. So yeah, because some of you maybe are struggling with a specific part of chapter 8. Maybe you don't need this one, you understand this part already. That's why I'm making short videos, guys. Thank you and have a good day. Bye.